Okay, guys. So, what did your group come up with in terms of activation energy? Brenda, would you like to share what your group came up with?
Wait, what? Sorry, I'm like literally.
Okay, so what's different about the no reactions versus the yes reactions in terms of activation energy?
Oh, when the no ones have lower because they like don't have to have as high because they don't have to be reversible. That's what we.
So you think these have lower
Yeah, I think the non-reversible have lower.
and these have higher?
Yes.
Okay, let's look at it. Okay? And let's think about this, okay? When a reaction is reversible, what are the reactants in the reverse reaction? The products, okay? So usually we go reactant, product, okay? But in the reverse reaction, we're going to go the other way. Now, have you ever considered, and actually I think there was something on the review sheet about this, and I said, you know what, we don't really need to worry about it too much right now. The reverse reaction has its own activation energy, doesn't it? Okay? Like if we look on this diagram, I mean, outline it in green, if this is the reactant, then this becomes the line from which we start.
Solid color.
A different color?
No, I said solid, like it didn't do anything.
Alright, here we go. This might be the good one. Okay, so we're going to start at this line and then go up here. This would be the activation energy of the reverse reaction. We can call it ear. Okay, do you guys get that? Now, for photosynthesis, compare the activation energy of the reverse reaction to the activation energy for the forward reaction. You can actually relabel this EAF. Okay, that sounds silly. Okay, all right. What's the activation energy for the reverse reaction like?
Short.
Is it more or less?
Less.
It's less. Okay, so over here, let's pencil in the reverse activation energy. Here, this would be the activation energy for reverse, and I'm actually going to put this up a little higher. Okay, whereas the activation energy for the forward might be here. Whereas here, the activation energy for the forward is here, but the activation energy for the reverse would be here. E sub A reverse. Which do you think is easier to go backwards? So, which diagram? With a low activation energy or a high activation energy? With the low. This one is easier to go in reverse than this one. Look at this. Look
So
at
the
all
graphs
of
are
that.
switched.
Yeah, the graphs.
Yes. So, thank you, Brenda, we got on the right track. So think about activation energy and what can reverse and what can't. But the reversible reactions are going to be the ones that don't have as high of an activation energy for the reverse reaction. Okay? Yes, Alex.
It's easier for an endothermic.
That's what it seems like to me. Did you guys hear what Alex said? So perhaps it's actually easier for endothermic reactions to back up. I'm going to kind of put that in the back of my mind, and as we go through reactions and start looking at what is favored, I'm going to kind of test that theory. Just like here, we had our no's and our yeses. You guys came up with an idea, and then you tested it by reading the rest of the list. I love that. Okay? Now, this reminded me, in fact, Star, I think it was you that asked this question about when we were doing kinetics, and we had the mechanisms, and we had the slow and the fast steps. And I want you guys to write this example down, and I want to remind you of it. It's pretty cool. Remember we said, let's say our reaction is 3A plus B yields C. That's our overall reaction. And let's say our proposed mechanism is A plus B yields Z. Z, did that help, Katie? Okay. Plus A, huh?
Are you collecting this?
Yeah. Yields D, and then D plus A yields C. First of all, does that add up to the overall reaction? Yeah, that's good. Okay, and then the pink as well. Okay, fine. All right. So this adds up. Now, what if I tell you that this is fast, this is slow, and this is fast? We got fast, slow, fast. We write our rate laws in terms of what?
Slow.
The slow step. So rate equals K times what? Z to the what? First. And A to the first. And does that look good? Or is there a problem?
Problem.
What's the problem? Say it louder, Magdalena. Z is an intermediate. We're not allowed to have intermediates in our rate law. Okay? No, it's not just that. What did we say we do when we have a fast step before a slow step?
So it'd be like A squared.
Remember we said that, in fact, there was a couple times where it said fast and reversible. Do you remember that? This is what they were talking about.
We take Z and reverse it to A to the A to the second, B to the first.
Exactly. We would replace in for Z, A and B, because it forms an equilibrium with A and B. So the rate law that we would write would be rate equals K. Instead of writing Z, we would substitute A to the first, B to the first. We would still have this A to the first, and then it would kind of simplify to A to the second, B to the first. Okay? Everybody kind of remember this? Okay. Now, if we were to draw the energy profile for this.
Why can't it be H to the third?
Why would it be 8 to the third?
Oh, I don't know, sorry.
You always look at the slow step, and whatever collides in the slow step is where you start. You don't worry about that fast step after it. Okay? All right. If we draw an energy profile, how many humps should I have for this mechanism? I should have 3 humps. Where should the tallest hump be? In the middle? The slow step. The slowest step is slow because it has the highest what?
Activation.
Activation energy. Good. So we start with our reactants. I don't know if this is endo or exothermic, so we'll go slow. I'm sorry. There. Maybe we do that. Okay? All right. So I'm trying to deliberately show the second step has a higher activation energy. So I want you guys to think about this. Okay? If after the first step we form this Z intermediate, right? Z has 2 choices. It can either keep going forward, which requires this much energy, or what else could it do? It could go backwards. Thanks, Frank. Right. It could go from, and the backwards only takes this much energy. Which do you think it's going to do? It's going to go backwards. And certainly, if there's not enough energy around, if it hasn't accumulated enough energy to get over this barrier, then it's going to go backwards. And we talked about this. That's why it forms an equilibrium. It's just kind of waiting to get enough energy to go that way. Okay? So it does that. Does that make sense? So that's how this whole reverse thing kind of comes into play. All right. Now what I'd like to do is I'd like to do a demo. Okay, this is pretty cool. I want you to write this reaction out a little bit bigger on your paper. We've got, and this is a reaction, this is a little demo with cobalt chloride. Cobalt chloride is CoCl2. When you dissolve that in water, are these going to stay together?
No.
No, what's going to happen? Paulina, what's going to happen here? Yeah. I added some more to your name, didn't I? I threw you off. Okay. Is it going to stay together, Paul?
No.
No. So it's going to break apart, right? So what's one of the ions it's going to form? Yep. CO2 plus. What are some other ions that it's going to form? Cl negatives, and they're not going to be. They're going to be kind of free floating, right? what happens when this gets in a beaker with water is that cobalt ion actually kind of gets complexed and surrounded by water molecules. So it looks gross, but it's really just our cobalt-2 ion surrounded by waters. Okay? That's the first part of that reaction. Now, what's cool is that usually there's 2 chlorides. What we found, this is a cool reaction, if we can introduce a few more chlorides, then, and this is pink. Cobalt solutions typically have a characteristic pink color because of the cobalt ion. Okay? If we do this, we can make it form a COCl4 ion. It's like the chlorides come in and displace the waters, and they surround the cobalt. Cobalt's 2+, each chloride is 1 negative, so all together, this ion is 2 negative. And then, of course, your waters got displaced. Okay? And this is a blue color. Okay? And remember, this was in the list of reversible reactions. So all of these, if you copied down some of these, for all of them, put the backward arrow as well as the forward arrow. They were all reversible. So I'm going to add the backward arrow here. Okay? And it's going to go back and forth. It's pretty cool. Yes, Alex?
So if they're reversible, what's keeping them from going right back and just stalling the reaction's results?
Probably because the activation energies aren't such that it's forcing it to stall in one place rather than the other. That's my best guess to your question. Okay? So it's about that. I really think it's a balance of activation energies in a sense. Okay? And actually, what this forms, in fact, what all of these new notes are about is equilibrium. Yep, equilibrium. And we're going to discover what equilibrium actually means. A lot of people mistake equilibrium by saying that you have equal amounts of each of these. That's not the case. Every reaction has its own balance point, but once it reaches that balance point or that equilibrium, it stays there for that reaction. Okay, and every reaction is different. Okay, so what I'd like to do right now is I'm going to show you this reaction, and then we're going to talk a little bit more about it. You know, you can keep filming. Okay,
But turn
so
around.
if we look over here.
Turn
Yeah.
it around.
Yeah, turn around. All right,
We're all on the video now.
and you can move anywhere you need to. Okay,
There
so
you are.
Here is the cobalt chloride solution, okay? And I'm just going to kind of dilute it and make it a light pink, okay? So here it is, all right? I'm going to actually pour a little bit out just so I don't have to use so much stuff. So here it is, and actually this is what kind of freaks people out a little bit. There is actually some of the blue ion in here, okay? Because I've introduced some chloride. There's some of the blue ion in here, but right now it looks like there's more pink than blue, so that's what your eye is seeing, okay? So the big thing I want you to get with equilibrium is the reaction never stops. Because you know what? Do molecules ever stop moving? No, not unless we got to absolute zero and, oh, we can't get there, right? Okay? So they're constantly moving, and it's constantly going forward and reverse, okay? Now, I'm going to force it to have more blue ions so we can see the blue, okay? And I'm going to use hydrochloric acid as my chloride source, okay? So I pour this in. And Wookie! I know, it's a pretty blue. Who plays Life? You know when you put your little pink people and your blue people? This looks like the blue of Life. Okay, all right. So, what we've done, if you look over here, is... Gotta keep up, Mom. Okay, is I introduced more chloride, and so it made it shift over to where there were more blue ions, and that's what we could see. Okay? This whole shifting thing was discovered by this dude named Le Chatelier. How many of you guys remember that name from Chem 1? Okay? All right, write this down. Okay? And Le Chatelier noticed this, and he really started to study it so that we could come up with a way to predict reactions using this principle. So he came up with Le Chatelier's principle, which basically says reactions at equilibrium, and only reversible reactions can form an equilibrium, okay? Reactions at equilibrium stay at equilibrium. That's kind of the simple phrasing of his principle, okay? And so what that means is reactions will shift, and they'll either shift forward or backwards, okay? Forward or backwards to relieve a stress. Okay, and what are the stresses? Well, I just stressed it out by adding a whole bunch of chloride ions. Okay, you can stress it out. Well, let me ask you, how could I stress this out in a different way? Maybe to see the pink. Add water. Okay, let's try adding water. Jordan is over here saying, heat it up. You know what? It's on a hot plate. Maybe heating it up would stress it out. And actually, we're going to discover tomorrow what that will do. And that's a great idea, Jordan. We're going to do that first thing tomorrow because I want to be able to develop it fully. Okay? So, let's see about the water. Let's see about the water. Okay. So, what I'm going to do is, I'm just going to use a little bit of this so I have room. And here we go. Here's the water. There we go. There's the pink. And it's so dilute. Okay, maybe this. Add the water. How much water do I have to add? Oh, not so much. Okay, there we go. There's the pink. Okay? Isn't that cool? Okay? So I've stressed it out. So the instant that I added the water, I got it out of equilibrium. And then it said, what am I going to do about that? Okay? And so it fixed itself by shifting to where the water wasn't to get back to the balance. Now it's at equilibrium. So the split instant that I added the hydrochloric acid that time, or the water, I got it out of whack. And then it fixed itself. And remember, all reactions can do is react. Okay? But reversible reactions can react forward, or they can react reverse. Okay? Does that make sense? Okay. Now I'm going to develop this a little bit more because right now you're probably still wondering, what is this balance? What is this equilibrium? What is this stress? And I still have more sense to make out of it. Yes,
I
Michaela.
have a question. Chem 1, when you were doing titration,
Yeah.
was that just to find the equilibrium point between those two?
No. The titrations, if you look, it's in the no category, the very last reaction. We were adding a base and an acid, and that went all the way. The pink color was that phenolphthalein. Now, actually, the phenolphthalein itself turning pink was a side reaction that you could call an equilibrium, I think. We'll talk about it more when we get there. Okay? All right, but that's what the pink is. Because you're seeing the pink, you're thinking, oh, what have I seen pink before, right? Okay. All right. So here, let's look at what this whole equilibrium stuff is. Okay? And what is equal about equilibrium is not necessarily these amounts. The amounts really can change. What Le Chatelier and other scientists that started studying equilibrium and reversible reactions discovered is that there is this constant. If you put your reactants and products in a certain ratio, you will always get the same constant. It's kind of like when we discovered the R in the ideal gas law. If you always put PV over NT, you get the exact same number, that 0.0821 number. And that was kind of freaky and cool at the same time when scientists discovered that. They discovered the same thing with chemical reactions. And this is how it looks, okay? So if we have an expression and its products the concentration of products raised to some power over the concentration of reactants raised to some power.
How is this related to a rate law?
It's not. It's going to be, these, I'm going to show you exactly how to get the exponents. We're not going to have to study any data, okay? So stay tuned, okay? This K is what we call an equilibrium constant.
So K has many different things.
Yes, and that is why in the last chapter when some of you started off writing big K's for your rate constant, I said, no, big K means something else. You have to make sure it's a little k. Well, here was the other thing, a big K. All right? Now, let me give you an example reaction. I'm going to make something very generic. Let's say A plus B yields C plus D. It's a reversible reaction, and the little letters, the lowercase letters, are the coefficients. This is what's awesome. All you do is you're going to say the products are C, and we're going to raise C to the C power. The other reactant is, the other product is D. We're going to raise it to the D power. And we're multiplying those. We don't usually write the multiplication sign, but just know if there's no kind of punctuation there, it is a times. It's like putting two parentheses together. You put this over the reactants, A to the A, B to the B. Is everybody with me?
Yes.
Now, the reason why we can just use these is because we're not talking about kinetics and speeds of reactions, and we don't have baby steps that are affecting things. I mean, these might occur in baby steps, but what we're looking at is totally amount. So this is back to stoichiometry in Chem 1. That's why we can just use the coefficients. Okay? Now, this is the cool thing. C doesn't always have to be, let's say, 2 molar. It can be 2 molar, 1 molar, 0.3 molar, whatever. But C times D to over A times B raised to their exponents are always going to be the exact same number for a particular reaction at a particular temperature. It's very cool. So you can either go into lab and figure out the K, or what we do a lot of times is we look up the K. But we can use that to solve things. Okay? So, now, let's consider states of matter, because we're going to have to pay attention to that. There are 4 states of matter: solid, liquid, gas, and aqueous. Which one do you think of as relating to concentration the most?
Aqueous.
Aqueous. When we talk about solutions, right, we're talking about an aqueous solution. We can have a 12 molar hydrochloric acid solution, a 2 molar, a 0.3 molar. That's very variable. What other state of matter can we easily change the concentration of, or the number of moles stuffed in a certain volume?
Gas.
A gas. You're absolutely right. And in fact, another way we can set up a K is by just straight up using pressures. And it would look like this. Pressure of C raised to the C power. Write this down. Pressure of D raised to the D power. Over partial pressure of A raised to the A power. Partial pressure of B raised to the B power. Technically, we call those K's that we get from pressures, we call them KPs. P for pressure. Sometimes you'll see this, instead of just K, they'll put KC, because we used concentration. Sometimes they'll leave it as K, or they'll put KEQ. That just means equilibrium constant. You know what I mean? You'll see lots of different types of Ks. All right? And these numbers aren't necessarily the same. We'll learn tomorrow how to convert between a KC and a KP. Okay? But, all right, so we've got aqueous and we've got gases. What about a solid? Do you think of concentrations with solids? Not really. A solid is like a pure thing, isn't it? Can you have a different concentration? No. So, if what now? If you dissolve it, it can, but then you're talking aqueous, right? So if it's solid, what were you gonna say?
Can't you heat it up a little bit so that it has a little movement? Doesn't that kind
Well, like
of, so that
alloys.
change?
Yeah,
Like
that's
when
what I'm saying.
metal rails
You didn't
get a
see
little
that.
heated up, they expand.
Okay.
Like the density changes.
Oh, I see what you're saying. But it's still, like in terms of, like if you're talking about a solid, you're pretty much talking about a pure compound or a pure element. And so
Where's the machine?
it's not like it's going to change that much. Now, I know last period they brought up alloys, right? Because like if you have iron mixed in with carbon and stuff like that. And so we're going to tuck that away and I'll think about it some more. But for the most part, solids can't really change concentration and liquids can't either. I know a lot of times, in fact, when I asked the question earlier, most of you said aqueous, but I heard a couple people saying liquid. Most of us, when we hear liquid, you guys are thinking of what you see as solutions. But pure liquids like water. Can water get any more concentrated than water? No, water is water, okay? And you're not used to seeing pure liquids like ethanol. You could have pure alcohol. Usually we see a 95% solution, so it's just a high molarity, okay? But if you had pure alcohol, it would be the same concentration always. So, solids and liquids stay constant. So, we do not include in a K expression. That's very important that you know. Because they're constant, it's almost like we lump them in with the constant. Okay?
What does it say before stay constant?
Solids and liquids stay constant, so do not include them in a K expression. So let's practice. Water is a liquid. This is an ion that dissolved in solution. So is this, and so is this. So if we were to write a K expression for this reaction, what would I start with? What would go on top? CO what?
CO4.
Does everybody agree that this product would start? And it doesn't really matter what order. We're going to start with products. So we have COCl4, 2 minus. To what power are we going to raise it?
1.
To the 1. It has a coefficient of 1. Are we going to include the water?
No.
No, because it's a pure liquid. Okay? All right, so now we're going to go to the denominator. What are we going to put there?
COH2O.
COH2O, 6, 2 positive. We're going to raise that to what power?
1 for
To a 1. And what else?
Cl negative.
Cl negative raised to what power?
4.
A 4. Okay? And that is the equilibrium expression. Okay? And let's say that I told you, I don't want to get too bogged down in the numbers, but let's say I told you the K value I looked up and it was 1 times 10 to the negative 3. First of all, if you have a K that is low or a lot less than 1, what does it seem to favor? The reactants. If you think about it, if it's always products over reactants, and you have a small number, you either have a lot of reactants or a few products, right? So small k's favor reactants. How about big K's? They favor products, okay? All right, so if I say it's 1 times 10 to the negative 3, okay, it forms an equilibrium. Now, if I think about the stress that we did in the beginning of the demo, we added, did we add this, Brandon? Did we add the chloride?
Yeah, we did.
Okay, so if we added the chloride, so if I upped this number, what is it going to do to this value?
Decrease it.
It's going to decrease it, right? If I increase the denominator, I'm going to make this even smaller than it was, correct?
Unless Cl has molarity of less than 0. Less than 1.
Okay, Alex, no. Shh. Okay, all right. If we make this a bigger number, okay, if we make this a bigger number, That's going to decrease the value of K. Everybody with me? Let's keep it simple for right now. Okay? So, if our stress made this smaller, what does the reaction have to, how does the reaction have to respond?
Has to go.
It has to make this number get back to 1 times 10 to the negative 3. So by adding chloride, I just dropped the number. So, what do I need to do?
Increase the top.
If I can increase the top, and guess what? The only way to increase the top is to take some of that chloride I just added away, right? So if I increase the top, won't I have it climb back up to the constant? And what did you observe when I added the chloride? Where did it go? It went blue, and that's the top. Does everybody see that? Okay. Now, here's the trickier one. What happened when I added the water? It went back. But is water in the expression?
No.
So why did adding water
Pure.
change it?
Because it was a liquid.
It is a liquid, but it's not in there. What does adding water to all the other chemicals do? It dilutes all the other chemicals. So, and look, these are both to the first power, but this is to the fourth power. So diluting this and then having to raise it to the fourth power is going to affect the equilibrium constant, right? This is going to be low. You're going to take a lower, so by adding water, I diluted all of these. This went down, this went down, this went down. But this one, because we raised it to the fourth power, was a bigger down than everything else. So if you decrease the denominator, what happens to the overall value? If you make the bottom smaller, it makes everything bigger, right? Look, 1/2 versus 1/8. Right? If you make the bottom smaller, then overall it's a bigger amount. So if it was too big, what did it have to do? It'd have to get smaller, which means it has to increase the bottom and decrease the top. That's why it shifted back. Okay? All right. Tonight's homework is going to